In this lab, we simulated the orbit of a star around a black hole and used the star's motion data to predict the mass of the black hole. We also simulated a spacecraft approaching a planet-moon system. As the spacecraft approached the planet, the goal was to find initial velocity that allowed it to orbit both the planet and the moon in a figure-8 style orbit. Using computational modeling and Newton's laws, we were able to analyze these motions and predict the values needed for stable orbits. The purpose of this lab was to explore the boundaries of escape velocity and Newton's second law using computational simulations. There are two main goals in this experiment. First, we use motion data from a star orbiting a black hole to predict the mass of the black hole. Second, we determine the correct initial velocity required for a spaceship to orbit both the planet and its moon. By modeling gravitational interactions between objects, we could see how Newton's law applies to complex orbital motion. This law is based on Newton's second law, which states that the net force acting on an object is equal to the rate of change of momentum. In part one, we use Newton's second law to analyze the motion of a star orbiting a black hole. In part two, we use the same physics principles to simulate the motion of a spacecraft interacting with both a planet and a moon. In part one of the simulation, the system consisted of a star, and the surrounding was influencing the star's motion was the black hole located at the origin. In the first part of the GlowScript program, we use position data from the star's orbit to calculate velocity and momentum at different time intervals. Using these values, we calculated the change of momentum over time, which gives the net force acting on the star, according to Newton's second law. Using the magnitude of the net force and the distance between the star and the black hole, we applied Newton's law of gravitation to calculate the mass of the black hole. The calculated mass of the black hole is approximately 1.1 times 10 to the 34th kilograms. GlowScript Part 2, the second part of the simulation, we modeled a spacecraft moving near a planet and a moon. The gravitational forces from both bodies were calculated and combined to determine the net force acting on the spacecraft. Using Newton's second law, we updated the spacecraft's velocity and position at each time in the simulation. After testing different initial velocities, we found that the spacecraft needed an initial velocity of approximately negative 3.948 times 10 to the 7th in the x direction and 2.97 times 10 to the 6th in the y direction. The velocity allowed the spacecraft to orbit both the planet and the moon without crashing into either objects.